Okay, good afternoon. We've come a long way, huh? I hope you're feeling like your heads are bigger than they used to be. More stuff crammed inside. So I have an hour to summarize the whole course, which of course I can't do. But I'll try to put it in some context for you. Jordy is writing, it's okay, Jordy's writing about a review session for the final, which will be at the usual lecture time next week, but running 2 hours here. And there's a final exam that you should, an old final exam that you should take ahead of time, and that's what they'll be discussing at the review. Great. Anything else? No. Good. Yeah, come to the final, right. Final exam, all individual, the usual rules, 4 sheets of notes, usual 1 per chapter style. So one slice of what this course is about, just want to remind you, is programming paradigms. I don't know that I ever defined the word paradigm, but maybe you can get a sense from what we've studied of what it means. It's sort of a way to set your head to do programming. You say, for the purposes of this program, I'm going to think in such and such a style. And the main ones that we looked at were functional and object-oriented programming. We looked at both of those as abstractions, as sort of, here's the paradigm, and also under the hood to see how we implement those things. And we looked in much less detail, but just touched on client-server programming, which is very related to the question of parallelism that's the hot topic in computer science right now, and declarative this last week, also known as logic programming. Programming language people these days don't talk as much about paradigms as they used to, because actual programs in the wild tend to combine bits of different paradigms. But that doesn't mean just throwing things together any old way. It means combining them in a disciplined way where you really do understand what it means to write a function, something that doesn't remember its past history and always gives the same answer for the same inputs and so on. As a completely different example of this, when you take 61C and you're learning about how a processor works on the inside, you're going to see pictures that look a little bit like this. And so on. There may be like 5 or 6 or 7 stages that look like this, where inside the processor, there's not a lot of memory, not gigabytes, but a little bit of memory. There'll be the registers that are visible to the programmer, and some other internal registers, maybe hundreds of bytes altogether. And that memory feeds values into a cloud of functions. So there's going to be a bunch of circuitry that does various things, but the stuff in that cloud is all computing functions. In fact, it will be computing Boolean functions, the predicates, because The inputs are single bits, 1 and 0, like true and false. And there are just bazillions of those. And then after that comes another batch of state memory, and so on. And that whole thing is a pipeline. They're not going to call it state memory. They're going to call it registers. And they're not going to call it cloud of functions. They're going to call it things like adder, a multiplier. But it's what it is a cloud of functions. And then more registers and so on. So this is kind of in the hardware level, a combination of object-oriented paradigm with state and functional, not programming, but functional hardware. So these are ideas that are just going to come back over and over. The other big idea, the central idea, if I had to say in one word what's this course about, is abstraction. And if you look, nothing's on the screen because I didn't do this. Yep. If you look on the screen, you'll see a handout that you got back on the first day, which says, you're not supposed to understand this yet, but that was then, this is now. Now you are supposed to understand it. The book talks about abstraction a lot, but never actually defines it. And that's intentional because abstraction means a bunch of different things. So it's not easy to define. For the purposes of this handout, I picked the most controversial definition I could think of. So this definition is an attempt to wake you up. It says, voluntary submission to a discipline. So that's like joining the Moonies, except it's not like joining the Moonies because you don't do it for life. You do it for this program that I'm writing right now. So you say, I'm going to program functionally or object-orientedly or whatever in order to gain expressive power. That's a paradox. I'm agreeing to refrain from doing certain things because refraining in that way gives me more expressive power. You'd think it would be less expressive power. So if there's anything you've gotten out of the course, I hope you've gotten what it is I mean when I say that if you're programming functionally, or if you're programming object-orientedly, or if you're programming declaratively, you have more expressive power than if you just do the first thing that comes into your head. Okay? And that really is the big lesson of this course. Some programming languages, less and less these days, but still some, try to enforce a particular programming paradigm. So there are purely functional languages in which you can't change the value of a variable. There are object-oriented languages, like Java is one of them, in which there's no just procedures. All there is methods of classes. And so you have to make a class even if you're only going to have one instance of it, and so on. So all of these things, some languages try to enforce, but it's much better if the enforcement happens in your head. So if instead of fighting and pushing the limits of a paradigm, you're saying, how can I make this paradigm serve me? And then the rest of the handout, I'm not going to go over every single thing on it, but there's a bunch of them, is for various abstractions, what does the abstraction focus our attention on, and what does the abstraction hide from us? So in functional programming, the focus is on repeatable input-output behavior. That's the definition of a function. And composition of functions as the way you build complicated programs out of simple pieces, as opposed to first do this, then do this, then do this. So composition of functions is the big combining method for the primitive functions to get interesting programs. What's hidden is side effects, which are happening down inside the computer. And also hidden is the innards of a procedure once it's written. So once you've written a procedure, it's just as if it was a primitive. You don't look at it. You only look at what am I supposed to give it for input and what is it promising to give me as output. And the same is true for all of these things. Every abstraction focuses your attention on certain things and hides other things from you. And that also, the idea of hiding something from you, sounds like something you wouldn't want. You want to see everything. And some of you, maybe a lot of you, will remember having trouble the first time you saw recursion because you didn't feel like you understood it until you traced every step down at the lowest level. So you understood how it is that level 5 calls level 4, and that calls level 3, and that calls level 2, and you actually had to trace through all of that every time. And finally, I hope, you got to where you just trusted that recursion works. It's like that for all these things. It's not that it's hidden in the sense that you can't know it. It's not a secret, but you're not thinking about it right now. Because the whole point of computer science is to make it possible for you to write computer programs by thinking about the problem you're trying to solve, instead of thinking about, oh, this computer has 32-bit words, which means I can represent blah, 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 blah. You don't want to think about your computer. You want to think about the problem. Before there was computer science, there were computers, and you had to program them at that level of knowing what every last vacuum tube was doing. And then they invented programming languages, and that really was the beginning of the idea of abstraction, although they didn't realize it. The first higher than machine language level languages, like Fortran, the people who invented them thought of them as just a shorthand for machine language. So they were thinking machine language in their head and writing down Fortran. And that was helpful, but it became much more helpful when they, probably without even noticing, shifted over to thinking in Fortran. The same way when you're learning a foreign language, you start translating it to English in your head, and then there comes a time when you're thinking in French or thinking in Spanish or whatever it is. It's the same thing with abstractions in programming languages. So that's what we mean by hidden, that you could think about those things, but you've learned that it's more productive not to right now. Okay? So I'm not going to go through the rest of these, but you should. You still have this handout, and if you don't, it's in lectures/summary. And you should read the 7 little things that it talks about and just go through those and refresh your memory about some of the big abstractions we've talked about. Okay. So speaking of abstractions, this is a picture of computer science in terms of levels of abstraction. And there's a cloud up at the top, which is theory, which is, in a way, the most abstract of all, but it's not built on applications. It's built on mathematics. So it's sort of off to the side. So CS70 is, of course, in the mathematical foundations of computer science theory, and then the 170, 172, 174, that series is about theoretical computer science. We made a beginning of that the week that we talked about orders of growth, that this procedure takes theta of n squared time or whatever. That's one of the foundational pieces of computer science theory. Another one is the theory about what computers can and can't do at all, never mind how long it takes. That's called automata theory, and it's really fun if you like math. If you don't like math, you'll wonder what the point is. Maybe. But there is a point. As John Bentley says in Programming Pearls, remember the picture I put up about the Radio Shack TRS-80 versus the Cray supercomputer that came out of Programming Pearls? Another thing from Programming Pearls, a great book, is he says, knowing a little theory can stand you in good stead when your boss asks you to do something that's theoretically impossible. So instead of saying, gee, I don't know how to do that, let me go try, you can say, I'm sorry, sir, but that's just not possible. And you can point to where it says so in a theory book. Okay, leaving theory aside for a moment, there's this hierarchy of levels. This isn't anybody's official picture. This is just my picture of levels. Somebody else might draw it a little bit differently, but not that much. So up at the top, we have applications. This is the thing that we're trying to get the computer to do. And if we're lucky, we write our application in a high-level language. And typically, the high-level language is implemented in a low-level language. I think I talked about this a little before, but let me remind you, low-level is not an insult. High-level is not praise. They're technical terms. A low-level language is one that exposes how the hardware works to you, that lets you know, an integer is 32 bits wide, and we have these mechanisms built into the computer, and so on and so forth. And you can point to a particular specific place in computer memory and say, give me this. Whereas a high-level language tries to hide those details from you so that you can write your program in terms of the problem you're trying to solve. So Scheme is an example of a high-level language. C is an example of a low-level language. Java tries to have one foot in both worlds. It's sort of in between. And, there are benefits to that, too, because it means you can do the low-level stuff when you really have to, but you can ignore all that some of the time. Opinions differ on how good a design job they did. Let me just leave it at that. And then below that is the language that the computer actually understands, called machine language. And there's assembly language, which is sort of a human-readable abbreviation for machine language. They're basically the same thing. And there's a dotted line there because it's really the same level of abstraction as architecture, except machine language is the programmer's view of it, and architecture is the electrical engineer's view of what makes this computer a Pentium and that computer a PowerPC or whatever. Architecture is built in terms of circuit elements called logic gates. These are Boolean functions, things like and or and not. And everything else is built up out of that. Logic gates are built in terms of transistors. That's a big, this line between logic gates and transistors is a huge abstraction barrier because at the logic gate level, the hardware is well behaved. So if you look at a wire inside the computer, it's got a 1 or a 0, and that's that. At the transistor level, that's not the case. There's noise, there's bouncy switches, there's voltages that are in between the 0 level and the 1 level. There are all kinds of things. There's just little bits of randomness that come in, or interference from the machine next to the computer. Somebody's running the lawnmower outside or something. So all that messy stuff that electrical engineers have to deal with are at the transistor level. And the electrical engineers, through heroic efforts, provide us programmers with these nice, well-behaved, almost logic gates. I'm saying almost because even at the logic gate level, there's a little bit of thinking about hardware that architects have to do. For instance, if you take the output from one of these logic gates and connect it to too many inputs of other functions, its voltage drops a little bit and it stops looking like a 1 or a 0. So you have to think about the messy, real, physical world a little bit, even with logic gates, but much less than with transistors. And how do transistors work? Transistors work by magic, just like primitive procedures. So the way we teach you computer science is from the top down. So in 61A, we're programming in a very high-level language, and we're looking not at all at how computers work. 61B, you think a little bit about how computers work. In particular, in 61B, you start thinking about efficiency, a topic we just touched on here. But you're going to start to really worry about how long something actually takes in the world. And it's a little more practical in that way. But please don't forget what you learned in this course, because as I've said several times before, it's much, much easier to take a correct program and make it run fast than to take a fast program and make it correct. So start by thinking about the computation you're trying to do, and then think about the efficiency things, even in 61B. And then 61C, 61B is taught in Java, which is this sort of one foot in each camp language. 61C, they use Java briefly, but mostly C and assembly language, machine language, for the MIPS architecture, which is just chosen because it's simple, as computers go. And it takes you down a little bit into the logic gate level. But mainly, logic gate level is the architect people, 150 and 152. By the way, I should say, the actual pieces of hardware that you can look at if you open up the back of your computer, and you see one of these little black chips, that has, what are we up to, millions of transistors? So it's not like you're going to open up the back of your computer and see a transistor. Okay? But in terms of the design, that's sort of what you're working with. How transistors work is electric circuits, which is 40 and sort of the 140s. And I guess I should have written E14X up a little bit higher. I think it's the 130s or something that's actual device physics. So there's some double E classes on device physics, and it all starts with physics 7C quantum, which I don't believe in. So I think it's software all the way down. Okay, so partly this is to reinforce the idea of what abstractions are all about and why it's important. So if you're trying to write an application, you don't want to be thinking about logic gates. Okay? Partly, it's an answer to the question, can I take 61C before 61B? And the answer is, the official answer is, yes, you can if you speak Java. But there's a reason that they're in the order that they're in. It sort of makes sense as a sequence, we think. Some schools do it in the other direction. They start with how the architecture works because they think that if you start low and build up, then you'll believe each level. Like by the time you get to recursion, you'll believe in it because you'll see how the bits move around in the computer. But we start at the high end because we think we're putting our best foot forward, that we want you out there in the world to have as your first instinct thinking at a high level. And sometimes you do need to think lower down, but start high and work as high as you can. And that's how you're going to get the program written and debugged the soonest, even out in the world. Oh yeah. This technical meaning of abstraction, I don't know if I said this before or not, is different from what lay people mean when they talk about something being abstract. To lay people, the stuff in the middle that you can actually open up the back of your computer and look at, that's concrete. And both software and quantum physics are abstract. And it's not that that's a wrong definition, but it's not the one we're using. We're talking about what sort of structure is built in terms of what other structure. And it isn't, historically, I guess it starts with architecture and logic gates. Because before there were transistors, there were other kinds of circuitry that they built computers out of. And the pioneering work was done around here. And so they did kind of move out in both directions from there. But now that that pioneering work has been done, in today's world, everything is built on top of the level below it. Okay. Now for the secret of success. You are most likely in your career going to inhabit one particular level of abstraction most of the time. So maybe you'll be an application programmer, maybe you'll be a language designer, Maybe you'll do operating systems, which is sort of off to the side here. Maybe you'll do architecture, and so on. And that's fine. So you're going to have an area that you're most expert in and most comfortable with and have the most fun doing. But the engineers, and I'm including software people in this, the engineers who change the world tend to be people who are aware of what's going on above them and below them in the abstraction hierarchy. Because if you're designing an architecture, to pick something in the middle, your work is going to respond to pressures from above and pressures from below. I learned this from Dave Patterson, by the way. So the pressure from above is that the users of your architecture are going to want to do different things with it. So they're going to want to be able to handle massive databases in parallel. They're going to want to be able to do very fast 3D graphics. They're going to sort of make demands based on the kinds of programs people want to write. You're also going to respond to pressure from below because both limitations and new capabilities will come from the lower down level. For example, right now, one of the big constraints in computer architecture is temperature. And so the more gates you put into a circuit, the more heat you have to dissipate somehow. And at one time they thought, well, of course we're going to run into limits. There's the speed of light and things. But we're way short of the speed of light, and we're still running into limits because of heat dissipation problems. And multi-core processors are in part a response to that it's possible to build, because it's not just how many transistors, it's also how fast you run them. So they would build circuits that were faster and faster and faster, and that means they got hotter and hotter and hotter. And now instead, we back off a little on how fast each individual core runs, but we put a bunch of them in there. So the goal is a decade from now, each processor on your desk will look maybe not so different from how they look today, but there'll be 1,000 of them on your desk, or 10,000, all in the same size box is the idea. And because each processor will be running slowly, we won't hit the heat limit. So that's an example of responding to pressures from below. It's not just at architecture. At every level, when you design a programming language, even a high-level programming language, you have to be cognizant of the fact that the hardware people are giving you multi-core machines. And that affects how people write programs, even in your high-level language. And you have to try to abstract away the parallelism so that the users of your language can write programs still in terms of the problem they're trying to solve, rather than in terms of understanding how to divide it up into pieces. One thing we've seen like that is MapReduce. Right? MapReduce is a piece of software that deals with tremendous amounts of complexity in terms of things like load leveling and dealing with processor failures and figuring out where things are in the distributed disk system and so on. And it hides all that under a level of, well, tell us what the map function is and tell us what the reduce function is. We'll get the job done. So that's an example of not a programming language, but a library that responds to pressure from below. Pressure from above, of course, is the applications that people want to write. So Scheme, which started life as a tiny little jewel of a programming language that was stripped down and theoretically beautiful and could do all kinds of programming paradigms and everything, is getting more and more complicated as people start actually trying to write applications in it. And they start worrying about things like, how do you know whether the character that you just read from the keyboard is a digit or not? That used to be really easy. There were 10 digits, 0 through 9. But now there's Unicode, which supports different languages, different human languages. And it turns out different human languages have different kinds of digits. And so even just something as simple as that is now much more complicated because of the pressure to have programs that work all over the world in people's native language. So at every level that you work, it's very, very helpful if you're comfortable at other levels of the abstraction hierarchy, and if you sort of keep up with the literature at different levels, especially the ones right near you, but all the way up and down, really. So that's the secret of being someone the world will remember 100 years from now, is to be able to anticipate what your level of abstraction is going to have to do in a few years because of what people are doing now above you and below you in the hierarchy. All right, it's time for your problem. Okay, remember I told you to bring something to write on? So this is a binary search tree, right? What I want is range takes a binary search tree and two numbers, low and high, and it returns a straight linear list, a sequence, in order of the numbers in the tree that are greater than or equal to low and less than or equal to high. And furthermore, does it efficiently. So if I ask for the range, let's say 64 to 83. Okay, that's the range that I want in this tree. Okay, so I'm going to start by looking at the value at the root, which is 37. And I'm going to say, hey, 37 is outside the range. It's too small, right? Therefore, I'm not going to look at any of these at all. That's half the tree I don't have to look at. Okay? 37 is too small. I'm going to look at 72. That is in the range. So sadly, I have to look in both directions. But when I get to 81, oh no, well, let's do it this way. Better example. When I get to 81, I say, oh, that's too big. So I don't have to look at this guy, and so on. Okay? Go ahead, write it. I'll wait. Whoops. Who's finished? Wow. Nobody. Yeah. I'm sorry? You're supposed to return a straight list of the numbers in order. Ascending. Left to right, just like the tree. Now what do I say? that a hand up or is it on? No, you're on it. Now what do I say? Cons. That's what I say. Because it's one element. Ta-da. Okay. Why did I ask you to do this? Because I'm going to tell you a story about this problem. Quite a bit before you were born, I was teaching 60C. It was a long time ago. It's more or less the course that's now 61B, data structures. The programming language we used was C. And one semester, I gave this problem as a midterm question. Nobody got it. So, next class, I came in and I said, what's up with this? How come nobody got this? Oh, it was really hard, you know. And I said, okay, take out a piece of paper, the way I said to you just now, and write it in Scheme. And they all groaned at me because they hadn't seen Scheme in a year, you know, a year and a half, whatever it was. And, you know, that was back in 61A. Now we're doing this other course. What's with the Scheme? And I said, hush, write it in Scheme. And you know what? Not all of them, but about half of them were able to write it in Scheme in class. Or at least mostly write it in Scheme. Maybe they didn't get the append cons thing quite right. And they said, yeah, but that has nothing to do with what you asked, because you asked us to do it in C. And in C, we don't have all this abstraction stuff. So I said, you're supposed to be looking at both boards at once. Yeah. Never mind if you don't speak this language. It doesn't matter. Oops. Yeah, I do mean that. What am I doing? arm's getting tired. Whatever. Okay? And they looked at me and they said, but C doesn't have append and cons and left branch and all that. And I said, you know how to make linked lists? And they all said yes. And they said, well, you know, these are just simple procedures. You can write those too. Or not write them. I would have been happy to see that answer on the midterm. And it's, you know, it's a perfectly legal C program. And you do have to do a little more, you know, the same as in scheme. You have to define left branch and right branch and datum. So how come nobody in the class did it that way? Well, because they tried to write it with global variables and loops, and it just never occurred to anyone in that class, even though we're dealing with a tree data structure, to write a recursive function. And why is that? It's because in C culture, and sadly also in Java culture, real men don't write recursive functions. So every once in a while, I overhear a student conversation in which somebody refers to 61A as the scheme course. It's not the scheme course. It doesn't matter if you never see scheme again in your life. You are going to see trees. And if you believe in recursive functions, I don't care if you're writing in COBOL, you will get the job done better if you understand what a recursive function is than if you're afraid of them. Okay, thank you for a great semester.